So,
Okay.
guys, yeah.
I'll introduce you first. So our speaker today is Dr. Gyan here. He is an assistant professor at the University of Colorado in the US. Before that, he was a research fellow at the University of Michigan and at Singapore University of Technology and Design. His interests are in cyber physical systems and Internet of Things with application to batteries, vehicles, and manufacturing systems. Published a lot of papers and a lot of conferences and has a lot of patents. But to me, the work that I really find amazing is how he takes what you think of as a battery and converts it into something completely else. And so I met him at a conference in Orlando earlier this year, and I was so impressed. I said, you have to present in our seminar series. So I'm really happy that he's taken the opportunity to present to us, and really looking forward to the talk. So Liang, it's all yours.
Okay, yeah. Hello, everyone. I assume it's a good early afternoon, right? Or around noontime so for you guys. So my honor to be here to share this recent research. So we call it batteries beyond batteries. Okay, so I will get started just talking about this title. From the title, we're talking about the batteries for sure. We use batteries all the time, anywhere, almost every day, right? And most typically, we use batteries as power supplies. That will cover the first topic I will cover today. That is, when we're using battery as power supplies, we need battery management systems to improve the battery performance, to make people happier. This has been a long-term focus of my research. Here I show 2017, actually, that's the starting point since I joined CU Denver. But actually, I started work on battery management even before that. So, okay, that's the first topic, not very surprisingly, batteries as power supplies. But actually, another thing is, because we are using battery as power supplies, we do have a very strong and very intuitive dependency that is between the system operation and then the related power consumption. And if we can capture this two dependency, then what we can do is we can use batteries as sensors or actuators in order to monitor or even control the system operation. So this will be the second topic I'm going to cover today. Let's get started by talking about batteries as power supplies. Again, this is a relatively familiar topic for us when we are using batteries as power supplies. We want batteries to be good. And this good can be defined in different metrics. We want the power to be reliable. We want the, let's say, system operation to be longer. We want the battery lifetime to be long. We want battery to be safe. To achieve this different multiple aspects of optimization objective, we need battery management, and which I call it a typical cyber physical system problem. So because talking about the battery management, we always need to start from the physical space. That is, we have the battery, the system, the environment, anything physical. And then we need to design cyber solutions. That means computation, and control in order to carry out battery management tasks. And these tasks must be designed based on some unique physical or chemical properties of the battery. And then these tasks will be carried out in the forms of algorithms, talking about battery monitoring, battery charging, battery discharging, and thermal control. So this is the general approach. One thing we are missing here is user-centric. This is the difference between, hey, I'm from computer science engineering talking about battery management. What's the difference between ME people, battery science people, battery material people when talking about battery management? User-centric is a very unique requirement for us because we are not talking about only battery management. We are talking about management of the battery in our phones. We are talking about management of the battery in our vehicles. That means we can improve the battery performance, but this thing cannot be achieved at the cost of reduced user experience. So in the next, let me use this something we call it the relaxation effect as an example to show you how and why we need to take these battery properties and user behaviors into consideration of battery management. By relaxation, we mean just let the battery rest by reducing or even terminating the current. And even given a battery, if we stop the discharging current, what we can see is the battery voltage will recover to some level after the stop of discharging and during the rest. And similarly, for a battery that has been charging, if we stop the charging current, its voltage will drop and then converge to a certain level during the rest. This is the observation of battery relaxation or let the battery rest. And this opportunity, if we use properly, then offers us opportunity to improve thoroughly all these 4 different metrics talking about battery management. And then, again, a more detailed example, unexpected shutoffs of phones. Let's see how, if we use battery relaxation properly, we can address this issue, unexpected phone shutoffs in code. And here, just to be clear, by unexpected phone shutoffs, we mean the phone shut off when showing a remaining power that is larger than 0. Let's have a clear observation on what is this problem using some measurement. Here, what we did is we fully charged a phone from Sony and operated in a -15 Celsius environment. So as a result, what we can see is the phone shut off in less than 3 hours. And then when it shut off, the phone is display a remaining power that is 26%. After that, what did we do is we just moved the phone back to the room temperature to warm it up. And then we try to turn it down again without even charging it. We can see the phone operated for another 2 hours. Okay, so you see, what's the cause of this premature phone shut off? Something is definitely not right? To look deeper into this problem, in order to keep the phone on, the phone battery must be able to supply a voltage, and this voltage has to be higher than the minimum level. And we call this minimum level a cutoff voltage. And in this equation, you can see here, the key 2 parameters are IB and RB. IB is the discharge current of the phone or maybe the battery, and RB is the internal resistance of the battery. And it is very clear when we are using the phone that the current is dynamic. We cannot really control it. Okay, it's a changing value. And also battery resistance, the RB is also dynamic. It changes with many other factors, such as battery voltage, battery aging, and more importantly, battery temperature. Here we show some measurement. You can see very clearly cold temperature increase the resistance a lot. And if we know this 2-dimensional dynamics of this current IB and the resistance RB, let's put this 2 back into this equation on the right. We will see if we are actively using a phone in a cold environment, then there is a high chance this battery will suffer from a larger voltage drop over its resistance. And as a result, there is a larger chance the phone will shutting off before the battery is fully drained. This is a real problem. It's not a new problem either. So Apple has its solution, has tried to solve this thing in one of its iOS updates. The idea is not very surprising, is to reduce the processing power when the remaining battery SoC or remaining battery power is low. And then the problem is this update caused a side effect. The side effect is very clear that slow down the phone usage. And it slows down so much that the problem is user can feel it. And if user can feel it, user will not be happy, and then eventually cause Apple multiple lawsuits and a $500 million settlement. To help address this problem, this is our solution. We call it the battery-aware power management middleware, or BPM for short. I will just remove this bar, hopefully block something. Yeah, so it's a middleware. Okay, and this middleware in general consists of 2 components. The first one is during charging. When we are charging the battery, we want to use a concept called the duty cycle charging in order to profile the battery and to know it. And then based on the battery information, at the runtime, when we are using the phone, we do discharge control, which we call it battery-aware discharging. So let's see these 2 steps in a little bit more details. Duty cycle charging. The basic idea of duty cycle charging is to rest the battery between 2 charging pulses, and so we have the voltage during the charging, the 2 charging pulses. That is the resting battery voltage, and we can use this voltage to profile the battery to know the battery better. That's the idea, but the challenge is, okay, duty cycle charging. That means you need a longer time to complete the charging, and we cannot make users unhappy. So what we did is we trigger this battery profiling, this duty cycle charging only during overnight charging. Overnight charging is common, that's for sure, and also more important, it's long. So that means maybe let's say 2 hours longer, but actually this thing will be more acceptable for users. Then with this duty cycle charging, we have battery information. And then at the runtime, when we are using the phone, we incorporated this battery information into the discharge management. And in order to keep the phone on for a longer time, the discharge management we completed in 2 parts. The first part is we try to regulate or limit the average discharge current by regulating processor frequency. And here the keyword is maximum frequency, not the average frequency. That said, if it is a maximum frequency, there is a chance we don't affect the user experience at all. Okay, and then another thing we used is the peak current. So we try to actively inserting a resting period between the execution of 2 tasks to rest the battery a little bit. And if you remember in the previous slide, there is an illustrative curve. When we are resting the battery, the voltage got recovered. So that means it helps us to keep the voltage at higher levels for a longer time. So this is the basic idea of battery-aware discharge management. We have implemented this middleware on 4 phones and tested, and the results, of course, confirmed our expectations. That's 2 things. First one, address unexpected phone shutoffs, and the second one is extend the phone operation. So let's see a case study with a Nexus 5X phone. So the first result shows we can, using BPM, to reduce the maximum voltage drop over the resistance. And because of that, we can keep battery voltage above the cutoff level for a longer time. And as a result, the phone operation is extended. And then goes back to our initial problem, that is to say we want a more reliable SOC estimation or remaining power estimation, so we can avoid surprising users with these unexpected phone shutoffs. And you can see here, we can do that. And another more insights on BPM is its advantage is more when we are using the phone in a cold environment or like when we are using old phones. The first result we showed here is in cold environment. So compare the 2 cases. We have the same phone. We use it first at room temperature, and then in the second case, we use it in the freezing temperature. And then without our solution, without BPM, the operation time has been reduced by about 15%. And with BPM, we can reduce this shortening of operation time to about 6%. Another observation is for old phones or old batteries. And by comparing these 2 sets of results, we can clearly see a larger advantage of BPM when the phone or maybe the battery got degraded much worse. The last part on the evaluation or observation on BPM is the trade-off. So nothing is free. Okay, Apple tried to solve this problem by reducing the processor frequency that is similar as what we did. And so let's examine what's the cost. So in general, we can achieve a 14% improvement of operation time at the cost of about 1% reduction of processor frequency. So that means we want more reliable remaining power estimation, longer operation time, but we really minimize this degradation of user experience. That's the 1% here. A quick summary of BPM. BPM is a solution we designed to address the unexpected phone shutoffs, especially in cold environment. And the key design philosophy is to let the battery rest. And then following this, BPM uses battery relaxation to profile battery during charging and regulate phone discharge at runtime. And then lastly, the most important part actually is it has to be user-centric. That is to say, we cannot make the battery better at the cost of making users unhappy.
Can I ask you a question here?
Sure.
So, I mean, thank you. It's a very interesting approach you have here. How generalizable are these to like stationary batteries in home usage, for solar PV or for electric vehicles?
The property of battery relaxation exists in all lithium-ion batteries. So that's for sure. That's number one. I can guarantee. I'm pretty confident to say. So that means the opportunity will be there no matter what the platform is. But on the other side, how helpful this property will be for the targeted platform, it will depending on scenarios we are talking about. So on top of my head, what I can say is if we are talking about a scenario where the discharge rate is always very, very high, then actually this let the battery rest can help, still can help, but the improvement will not be on the extended of operation, but more like to say to slow down the aging of the battery. So it will be still there, the opportunity. But the key focus, if I was the one to keep looking on it, will not to say, hey, because I use this, I can make my car drive another 50 miles longer. I don't think that would be feasible because anyway, given the battery, there is a limitation. Yeah. So what we can do is to do it in some way to make it to achieve a slower degradation or aging process of the battery. So that's it. So, but go back to your question. So this property is there. By using this property, we can always optimize the battery in different aspects. The problem is how much a space we have for this optimization. It depends on the platform, especially the charging or discharging rate. Yeah. So that's something on top of my head I can sort of.
Yeah, I mean, so just to follow up on that, I mean, I think just some cars have so called eco mode of driving. You cannot have enough same level of acceleration, but I guess that makes the battery last longer. So we could also think of heat pumps being driven in an eco mode by the batteries, perhaps at night, and then that would extend that. And that would be an interesting direction for research. How do we operate home batteries in a way? There's also a question from Andrew Moore. He says, has the battery community explored redundant arrays of inexpensive batteries, similar to RAID for disks? For example, where you can have sleeping batteries combined with awake batteries and where we can use arrays of.
Yes, actually, that's a good question. I'm also reading the chat. So sorry, I may miss any questions on chat because when I'm talking, I cannot see that. But actually, that's actually very good question. If you remember, I started to say, hey, this is relaxation-assisted battery management is a topic, let's say, most of my focus since 2017. And I already shared before that, actually, I already started my battery management. During that time, that's the focus that is something we call it reconfiguration-assisted battery management. That's exactly the idea talking about sleeping batteries combined with awake batteries. Or maybe we can actively control which battery or which battery cells to use and which ones to rest. So definitely that will offer a more active opportunity for us to identify the chance to rest a subset of the battery in a large battery pack. So yes, challenge. I worked on it for a long time, since 2012, design some kind of reconfiguration circuit so we can control how to involve or incorporate the individual cells into the overall usage. The idea, people like it, especially from computer science people talking about algorithm design, a lot of, let's say, software side optimization. The key challenge, based on my experiences so far, is if you're talking about EV battery pack, high voltage, high power, you follow the idea reconfiguration battery pack, you need a circuit to actively adjust the battery connection. That means, hey, this kind of relay switches, they need to be high power because we are talking about driving a car. And if things are high power, they need to be large, they need to be expensive. It's difficult to guarantee the warranty. So those are the more on the hardware side, of, let's say, a circuit side challenge. Yeah. But after that, another just a quick one. Actually, this concept, reconfiguration, active reconfiguration to improve battery pack performance, we do have, based on my knowledge, we do have real-world usage. That's the Microsoft Surface. Surface, we have keypad, we have the tablet itself. Both of them, they have batteries. And then the time you connect the two, you are using the two batteries at the same time. And Microsoft do have some active control talking about how to use these two together. I think that paper appears in SOSP 2015 or 14. But we can well imagine if a paper appeared in 2015, then the technology is already there maybe 2 or 3 years ago. Yeah.
This is the software-defined batteries paper, I think.
Yes.
Okay, please go on. Thank you.
Okay, thank you. If we borrow the screenshot from iPhone, more specifically the battery health module of iPhone, then we can see what we talk about BPM, battery aware power management for phones. Essentially, we're talking about peak performance management. And we achieve it using battery relaxation. And battery relaxation, if you use properly, as I mentioned, can offers opportunity to improve or maybe provide all these type of functions. And actually, a key collaborator when we are working on this job is now a member of Apple's battery team. So let's stop our discussion on battery management here and try to revisit. For battery management, we need to monitor battery to collect the voltage, collect current, collect temperature. Based on this information, we want to make an optimal decision in battery management. And it is very clear, battery voltage, battery current, battery temperature is determined by, of course, the battery, but also by the system they power. And if this is the case, then it will be not very surprising. We already have the battery data. And then from the battery data, we should be able to tell something about how the system is operated. And because this idea, the batteries as sensors and actuators, and I will talk about this in the next. We are switching our platform. When we're talking about batteries as sensors and actuators in this talk, I will switch the platform from phones to cars. And the car is not electric vehicle necessarily. In general, it's all types of cars. So long on these cars, they have this 12-volt or 24-volt automotive battery that is traditionally used to crank the engine. So the philosophy is we believe, or maybe we feel, this automotive battery can be used as a physical channel for car or to monitor and control the car operation. Following this idea, two works we have done. The first one is on vehicle immobilizer, and the other one is on anomaly detection. Let's talk about the immobilizer first. So lucky or not, at least here in the US, we have seen a record high auto theft. This year, very likely. Okay, last year is confirmed. And this has cost almost 9 billion last year. And another thing is because auto theft is increased, also so is auto insurance premiums. And it is about a 30% since 2020. The key difference between these two lines, the blue line talking about auto thefts, some people may care, some people may not care, depending on your neighborhood, depending on the area you're living with. The red one, the orange line, talking about auto insurance, that matters for every single one of us, so long you have a car. 30% increase, that's actually not very, very less. And another thing, even make it even more worse, is auto theft is not just a stolen car. It's never just a stolen car. If a car is stolen, there will be many indirect negative impacts, such as the car could be used to conduct the secondary crimes. It happened 60% more last year in Colorado, and also 6 times more, I think, since 2018 in Colorado. Yeah, and also, so for example, identity theft. Anything inside the car is not secure. You're risking the identity and even access to your home. And another thing, more on the social side, is auto theft is a biased attack, a biased issue. It is unevenly distributed to the population. Here, what I showed is a comparison between the auto theft rates with wealth in 12 Colorado counties. A clear trend you can see is the auto theft that tend to attack the people who can least afford the views. Or put it in other words, auto thefts tend to attack people who need a car more. And why? Why we are seeing this significant increase of auto theft? is a key contributor is the vulnerable car keys or key fobs. So, and this leads to a very ironic fact. That is to say, the very solution we use to protect our cars from being stolen is now being used to steal them. Some of you may already saw this kind of videos or screenshot from news or YouTube. So typically, when people hacking steal cars by hacking car keys or key fobs, generally two approach. The first one is external wireless replay or jamming and replay. The second one is if they can get into the car, they can do something we call the key clone through the in-vehicle network. That is more specifically through the OBD2 port. And there are people saying you can get a dangle to do this on the black market with less than $25. So I never tried to get that dangle. Instead, what I got is software-defined radio. I also have a little bit of networking and communication background. So software-defined radio is a very often commonly used research device. And then I recruited a senior design team, undergraduate senior design team, to try out, hey, can you try to hack the car keys using software approach? And then they demonstrated the feasibility in 10 weeks. To understand more about the limitations of car keys or key fobs to car owners, we conducted a survey with over 600 car owners. We find 10 limitations here we listed, and then the top 2 is people don't trust it. People don't trust the car keys for auto theft protection. The remaining 8, okay, we can terminate it in different aspects, but in general, it is to say, hey, keys or key fobs, it's better than the previous generation solution, but still it's not convenient enough to use and maintain. And then goes to our solution. The limitation of car keys or key fobs is the cybersecurity, and also another not so good is inconvenience. Let's try to solve this. And this 12-volt battery offers the opportunity to do this. This is based on 2 observations. The first one is very straightforward. Without power, the car is not startable. It cannot be cranked. So, and because of this, if we were able to actively control the power capacity of the battery, we should be able to use the battery as an immobilizer, or maybe let's say actuator, to disable or enable vehicle driving. The second observation is between the battery and the people. That is to say, the 12-volt power line network of the vehicle offers a very good channel, physical channel, for the driver to send the authentication information to the battery. And because of this, the battery can be used as a sensor to collect the driver's identity securely. Why security is because this communication channel, this power line network, cannot be remotely accessed, cannot be accessed through the in-vehicle network. So that's more secure, less accessible. And by combining these two, we can see there is a chance we can use the battery as a control knob, or maybe as a design foundation to design an immobilizer. And the key idea is today this immobilizer will be in physical isolation from common cyber attack vectors. Following this idea, we designed a solution we call the BVIM, battery-enabled vehicle immobilizer, to protect the cars from stolen. And this BVIM consists of 4 functional parts. The first one is the driver authenticator, okay, to know whether this is a good driver or not. And then the second component is power controller. If this is a good driver, then the power controller will fully restore the battery's power capacity to enable driving. Otherwise, it will reduce the power capacity of the battery to disable driving. This is the immobilized authentication and the immobilization process. And to support this process, we have a set of anomaly detectors to detect if anything is wrong during this process. And if yes, we responded right now based on the design with a siren or maybe alarm. And also power supplies that can be recharged automatically during driving. The key design idea is we don't want users to maintain this hardware or maybe embedded module there. Install there and forget about it. The others, the 3 component, power controller, anomaly detector, and the power supplies, they are essentially designed as a circuit driven to ensure the reliability and also quick response. So in the next, I will talk more on the driver authenticator. And more specifically, we designed two such solutions, the first one and then the second one. The first one is something we call the behavior-based driver authentication. And the basic idea is the battery will respond to a given load with a very unique voltage pattern. The example shown here is if you're swiping wiper twice, we can see a specific behavior in battery voltage. And this specific pattern of voltage can be used as a fingerprint for the driver. And based on this, for the use case will be the driver can just define or customize their own behavior of these electronic systems of the car, such as swipe the wiper twice.
Yeah.
And do you have any questions? Okay. Okay. Yeah. Yeah. And then this will be the password. Then whenever you want to use the car, you just repeat this operation and then to authenticate the driver, him or herself. But the challenge is a lot. Okay, because this voltage varies with a lot of context factors, such as the background operation of the car. And also for some operation, it's very difficult for us to repeat it identically every time. And more importantly, batteries. The battery voltage varies with battery SOC, battery aging, and the temperature. So that's the challenge. And how we address them, we address them in 3 steps. The first one is we need to carefully extract and align the fingerprint. In terms of data science, this is related to the data cleaning part. And then the second part is the core component. We need to analyze the similarity in both the time and the frequency domain. And then the third part is update of the fingerprint properly. That as an example, here I show the calculated similarity between 20 different E operations of the car. And the fact that, let's say we can see very clearly, the highest similarity is always achieved between the same operation. This fact verifies the feasibility of this behavior-based driver authentication. And then if we go back to this, we can see the key idea here is, yes, it's the behavior or not. But actually a key nature is we are trying to reuse pre-built electronic component of the car, such as watch, such as wiper, such as window, or maybe lock and unlock doors. And this will inspire us if we have the opportunity to add some kind of customized electronic dongles or devices. We should be able to achieve better authentication. And this is our the idea of our second work in this direction. We designed a power line communication-based driver authentication system. And this PLC-based authentication includes 2 physical modules. The first one is a front-end dangle that will be plugged into the 12-volt cigarette port and to interact with the driver. And then there will be a back-end authenticator installed onto the battery to communicate with the front end and also authenticate the driver. And this communication, in terms of the software side, this communication system consists of 3 layers. My bad. The application layer talking about extraction and matching the code, modulation layer that's typical to handle the modulation or demodulation of the signal, and then including the physical layer, the circuit layer, to control battery discharge to form the desired current signal or maybe communication signal. The question maybe some of you already have is power line communication. I have heard of this for this concept many years ago. So why do you need another one? So put it in short is existing PLC designs is not applicable for us. First of all, if you're familiar with smart buildings, smart power systems, then you will be very familiar with power line communication, this concept. But the difference is most of the power line communication solutions designed for power grid, for buildings are not applicable for us because the power topology is totally different. And we do have a limited set of vehicular power line communication solutions. But even for those, still we are different. For this typical power line communication for vehicle systems, we are talking about achieving a communication between 2 or maybe 3 or even more peer loads in the power line network. But here, what we are talking about is to achieve a communication between a load and the power source, that's the battery. And then because of the battery, then we have a lot of additional problems that this traditional PLC channel doesn't have. For example, the voltage change. So challenges and the solutions. The first challenge, we use battery to form the battery information to form the communication signal for the PLC. Shall we use voltage or current? Okay, right now our design, we use current based on the observation of the fact that current has a faster response to load changes. And if this is the case, when we're using current as the signal carrier, then we can achieve higher data rate. Another one, you have the signal using current, then how large a current is needed. And very intuitively, if you use a very high current as a signal, then the communication is easy. Okay, it's very reliable, but at the cost of more power consumption. So we provide a guidance system, or maybe let's say experimental guidance, talking about given this system setting, how do you identify the best current that is minimum and also can ensure a reliable communication? Okay, we have the signal, then how to do the modulation. I use the MFSK here. Okay, it's one of the easiest one, and also with some kind of a optimally optimized, theoretically optimized settings. You have the signal, you have the signal modulation, you have the symbol, and then how long you transmit a symbol. The shorter, the better for in terms of authentication delay, but the shorter a symbol, the challenging for it to be accurately received by the authenticator. So again, a set of systematic guidance on how to identify this a optimal or maybe reasonable symbol duration is provided. It's not the end. We have more questions to be answered. For example, shall we design this communication system as asynchronous or synchronous? How can we add a little bit of encryption to provide a little bit of more security? How do we schedule the activation of this PLC module in order to ensure the availability of driver authentication service, but at the cost of at the reduced cost of the power consumption? And how do we detect the vehicle status in runtime so we know when to trigger this anti-theft protection? Solving this problem, we designed the BVM as an end-to-end solution. You already saw that we have a prototype, so that means those things can be installed on cars and tested. So we have a solution and compare with existing vehicle immobilizers. So we have different advantage, and of course, this table could be something just too much to introduce, to explain in detail during a presentation. So I will use this part to highlight. Three-dimensional of advantage compared to the previous or existing immobilizers. The first two are convenient. Oh, I believe there's a timing here. So the first two is the first two, I will just go this one. So the first two is convenience and security. Okay, we want to have a combination of the two. And the third one is not so straightforward, is universal applicability. That means we don't differentiate whether this is a gasoline car, hybrid car, or electric vehicles. All cars, so long they have this 12 volt or 24 volt, they can be deployed. And also we don't need to customize a lot based on which specific car you are talking about. Yeah, I will go back to this presentation mode. In-field test. We have this prototype actually for 3 versions already. We tested in total right now on 11 cars, including all types of cars, gasoline cars, hybrid, and electric vehicles in different conditions. The conditions defined as background operation, temperature, battery voltage, and age. The performance, talking about driver authentication, is pretty good. Worst case, 99.9% accuracy. Here is a short demo. Yeah, so that's a quick demo. We doesn't really include everything. For example, our anomaly detector, power supply, automatic recharging, that part is more on the function to disable or enable vehicle driving based on the second factor authentication solution. So, and then you can see in the demo video, you can see this is a second factor authentication solution, right? But actually this technical wise, or maybe the solution can also be used to deliver BVM to protect or maybe to control the entry of cars, that to say to unlock or lock the doors. And with that, we have already verified, but of course you can see this is a very much a laboratory setting. No one will want to have a car look like this. Okay, too ugly. But function wise, everything is tested. And if we have this two-dimensional thing, first thing is entry control, and then the other is immobilization, then we can see this BVM solution has the potential to replace car keys, not only improve them, but actually replace them. And if this is the case, we will have the potential to open a totally new era of vehicle usage. That means we don't have any keys or key fobs, and we don't need to carry anything. And this will be particularly important for fleet management when we are talking about hundreds or even thousands of cars you need to use. This technology has made multiple broad impact, including some a winner of Lab Venture Challenge. It's a competition in Colorado, statewide competition, talking about the transition of university research. It helps us with connecting and partnership with different parties, including governmental ones, for example, auto theft prevention authorities, and also industry, specifically automotive supplier. Actually, it's in Europe. It's a Germany-based company. And also a lot of media coverage. The second topic we explored on the battery as sensor and actuators is anomaly detector. This one I will just briefly talk about the idea. When we are talking about anomaly detection for cars, more specifically, we are talking about to detecting wrong sensor readings inside the car, because wrong sensor readings could potentially lead to control decisions. And this is the risk not only for cars, but essentially for all engineering systems. And in the idea of is cross-validation, okay, to detect the wrong sensor readings based on cross-validation. And the cross-validation, the concept is not new. In one of the very well-known textbooks or Bibles on automotive electronics, it is referred to as model-based sensor failure detection. But there's a challenge, also acknowledged in this book, is if we want to implement this idea in practice, the question need to be asked is, do we need additional sensors? Do we need how many such kinds of sensors? Do we need to modify the car? And more importantly, cross-validation. Okay, we are comparing the two, and if something is wrong, which one is to blame, which one to trust? We answer this question by using the battery as a root of trust. The basic idea is, first, battery has a strong dependency because of power consumption or power supply, has a very strong dependency with a large number of vehicle modules. That means we can use battery to potentially diagnose a wide range of sensor anomalies. And the second one is battery information is easy to be collected. There's an example talking about how can we use battery voltage as the information to determine if something is wrong in engine RPM. In theory, I will not go through the details, but in theory, remember the in theory part that indicates something may not be true. Okay, in theory, if we are driving a car faster, we have a high power generation, more power generated from the alternator, and then we will have more power to charge the battery. And if that's the case, we will expect a monotonic relationship, higher RPM, we can observe higher voltage. And then in practice, how this theory is observed is something like this. We drive the car for 40 minutes, we plotted the scatter plot here, we are expecting a monotonic relationship, but hey, almost not there at all. Okay, again, this because in the above diagraph, it's more like a conceptual model. A lot of practical challenge is not considered at all. For example, the voltage control during charging of battery. But this is not a showstopper. If we dive in deeper into the same set of data, we do able to identify a very reliable relationship between the voltage and also engine RPM. And this kind of very reliable relationship can serve as a foundation for us to detect engine anomalies using battery voltage. Then we know a single case. Okay, we can use battery to say something about if engine RPM is wrong or not, but a car's operation is monitored by hundreds of different sensors. How do you know, given a sensor, hey, can you do it? Can you detect anomaly there using the battery or not? So to clearly answer this question, we proposed a two-layer graph model to abstract or capture these internal dependencies of vehicles, and together with the algorithms to generate this model based on the operational data. So we implemented the whole idea and tested on 4 cars, and the result shows over 86% rate of detecting sensor anomalies. If we combine what we have talked, okay, immobilizer and anomaly detection, using some terminologies in cybersecurity, then we can see, talking about immobilization, essentially we are talking about driver authentication and access control. And if we're talking about anomaly detection, then we can use a similar approach to serve the purpose of intrusion detection. And in this way, we can see by combining these two projects, we can provide a multi-layer, that means comprehensive cybersecurity management system for cars. And this is a battery-enabled one. And this is particularly important because automotive cyber incidents has increased more than tripled since 2018, and this cybersecurity management system has been mandated in Europe in 2021. And also talking about the research, we hope this type of research can promote or maybe trigger people more thinking on the physical security side in a ever more connected world. Okay, because everything is connected, that's good, that's convenient. But if you're talking about cybersecurity, then there'll be more risk. And then maybe now is the time to think more on the physical security in order to provide a last layer or maybe worst case security protection. A summary and a research vision. So a typical nature of cyber physical systems is the system interact with multiple system domains. For example, I listed here power, environment, user, data, software, memory, sensors, actuators, that's hardware side. And when we are talking about battery management, specifically this relaxation-assisted battery management, we are talking about, hey, we find there is a relationship between the environment, cold temperature, power, okay, of course, battery supply, and also user behavior. And then by jointly consider the dependency between these three domains, there is the opportunity we can deliver a better solution talking about battery management. Similarly, when you're talking about this battery-enabled vehicle something, immobilizer and diagnostics, we are talking about using the physical dependency between the vehicle power consumption, driver behavior, and also the vehicle's monitoring data. And if we can see that essentially the research concept is we observed some set of invariants across different system domains. And if we jointly consider this different cross-domain system invariants, there will be unique opportunity for us to reliably or maybe trustworthy to a solution to improve system monitoring and control. So this will be our research vision, and our next, right now what we are trying to do is to extend this concept cross-domain system environments to different platforms, not only on mobile devices and cars. So that's all I have for today, and I will be very happy to take any questions. Thank you.
Okay, questions? Oh, sorry, can we do it again? Oh. Okay, so I would like to push a little bit on your system invariance vision that you had in the last slide about the cross-domain.
Yeah.
In order to come up with these invariants, you kind of need to understand the system at multiple levels. When you need to have the understanding of the physical and the middleware and the software and the user and so on. But most people are sort of in a silo. They just see one aspect of the system. So how do you come up with the ideas of what a cross-domain invariant should look like?
Talk to people, make friends, talk to people, not only talk to say, I have this problem, but more like to say, hey, we are friends, let's just talk. And in many of the cases that I feel that's a very effective way for us to have a click to say, hey, there is a good idea. That's number one. And also another thing talking to people at with more specifically with different background, of course, is learning, right? So, hey, I have this problem. It seems I need some knowledge on power, real hardcore power knowledge. Of course, I believe as a well-trained student or well-trained researcher, we can learn everything given enough time. But then if you have someone who is this kind of domain expert, talk to them, collaboration, that would be a very effective way for learning to improve ourselves. Yeah, but anyway, that's a good question. Talking about the cross-domain system environments, that means for this type of research, definitely not only CS. Actually, many people have asked me, hey, your research seems not from a computer science department. So that's very true. And then that it's just that we need to be more curious about what's happening on the other side of the world, and then try to see, do we have any opportunities to work together and then improve the system better?
Maybe I can give you the Cambridge answer to this. It is here we go to the pub at the end of the
yeah.
Everybody has a beer, and they're all experts in different things, and many ideas here come from the pub. So going to the pub is actually not just a social thing; it's actually a place to develop cross-domain system invariance. So I hope we can one of those when you hear it. And any other? Yeah, Michael.
On the going back to the kind of duty cycle for the battery life issue. What's the kind of frequency response? Like, what impact does the kind of, like, I could keep it off for 50%, but does it matter if it's like half an hour off, half an hour on versus 10 milliseconds on, 10 milliseconds off?
Good question. So because this is a very good, very technical question, let me go back to a good example to support our discussion in this line. So I think this let's say duty cycle, right? This is related, not exactly the same thing you're asking, but anyway, this is a good reference for us to support our discussion. So the frequency domain behavior is a very important factor to consider. Do we really need to rest the battery for 1 hour? If yes, then they're almost useless because there's almost no chance we can do that in practice. So in theory, you can see here, we essentially are talking about this curve, this duration here, how long a rest is sufficient. Talking about the battery material guy, battery science, there is specific ways to determine how long a duration is enough. And if I remember correctly, those are in the range of tens of milliseconds. Of course, different types of battery could have different numbers. Okay, but that's in the range in tens of milliseconds. And then this, for example, 20 milliseconds, this number can be identified based on this voltage curve. Okay, we have this voltage curve I'm talking about here, the voltage curve I highlighted. Given the measurement of this current voltage curve using regression, using fitting, we can estimate the needed battery, let's say, properties in order to determine this 20 milliseconds. When I'm talking about, I always talk about battery resistance. It's more like a very relatively high level, abstract or simplified terminology. But that resistance can be replaced with a lot of different more detailed battery properties. Okay, that's number one. So the best I can give is 20 milliseconds, maybe, for example. Okay, that's on top of my head. And in our research, in our work, in most of the case, we make it much longer. For example, in this duty cycle charging, eventually what we did is the rest period, you can see here, is 100 seconds, if I remember correct. Yeah, it's 100 seconds. Okay, and also I have also did some other measurements just for measurement purpose. There's no application support at all. In those measurements, I just let it rest about 10 minutes or even 30 minutes. Okay, actually there is another work. All the observation is based on a 30 minutes rest relaxation period. So let's go back to the question, how long a resting is needed or maybe is sufficient. So in theory, we have a theoretical way to identify it. In practice, I feel we can always have the luxury to make it a little bit longer without causing too much trouble in the user experience side. Yeah.
Great.
So then we can make sure it's sufficient. Yeah.
Milliseconds is interesting, right? Because at that point you could, like with video games, for instance, you don't want to impact responsiveness or latency, but you could scale back resolution and kind of, you're almost back into frame resting periods at like 10 milliseconds.
Yeah.
So that.
And also another way is to say, it's more like to say maybe tens of milliseconds can recover or maybe rest for example, 80 or 90%, right? But if we want to keep resting up to 99%, maybe this additional 9% that takes, for example, hours long. So that's another way to view it from a system or application point of view. Do we really worth it? Do we really need it for this kind of rest? Yeah.
So maybe I'll raise Andrew's question, and we also need to end. So Andrew's asking, can you give an insight into why we need a relaxation in the first place?
Yes, I can talk in a relatively conceptual way. I know where to find and then refine my story using very scientific battery terminology, but I don't think that's needed. So in general, when we are using battery, either charging or discharging, we are triggering chemical reactions inside. That means we are injecting or maybe causing a lot of dynamics, chemical reactions inside the battery. And then by resting the battery, we mean we're cooling down the chemical reactions inside the battery. And then that means the time when we are resting those things, when we are let the battery inside cooling down, we have better understanding on what's actually happening. A non-scientific, but I think a very helpful conceptual story is, think about I'm having a glass of beer. When you're pouring your beer, you will have a lot of bubbles. Those things, yes, you still have your whole glass full, but you don't have a lot of beers. Maybe more than half of them are those bubbles. Okay, you cannot really enjoy the taste. And then you need to let it cool. And so after all those bubbles are gone, then you know how much power, how much juice you actually have inside the battery. So yeah, I hope that's good enough to trigger some additional thoughts. And if you prefer a more scientific explanation, we can talk more on offline. That is, send me an email. We can keep talking about that, because that involves too much of battery details.
So let me stop with that. Actually, the other explanation I heard, which is similar, is that when you are removing power from a battery, the ion depletion happening in the electrolyte, and then you need to have diffusion in the electrolyte for the ions to restore the equilibrium back. So essentially, it's a zone right next to the cathode. The anode is depleted of ions, and so and then when you let it rest, the diffusion of the ions restores the equilibrium when you get the charge again. So that's, if there's like ion depletion at cathode, I think, or anode, I can never remember. Is actually that might help you understand and explain this as well. So, in any case, thank you very much for your talk. I'm afraid we do need to stop, but thanks a lot for getting up early and sharing these wonderful ideas with us. I look forward to seeing you and having the beer and then relaxing after that.
Yeah. Okay. Sure. Thank you. It's my honor to be here. Yeah. Bye.